Okay, this is example 4 in your book on page 63, and in order to be prepared for this example, make sure you read about Bernoulli, the Bernoulli equation, because, well, you need to understand that in order to do this problem, and it's one of the concept questions as well. Okay, so in this problem, we're given this differential equation, which happens to be, right, example 2, which we already solved. And remember that this differential equation is neither separable nor linear. But we did learn in example 2 that this was a homogeneous differential equation. So maybe recall, so this is neither separable or linear, right? But, right, it is homogeneous, homogeneous. I've heard both terms. I believe it's homogeneous, but if you say homogeneous, that's okay. So we have this first order differential equation, right? It's not separable, not or linear, but it is homogeneous. So recall in example 2, when we solved this differential equation, we obviously used the substitution method, and we were able to separate the variables, and we obtained a solution. So we should obtain the same solution in example 4, but here we're just going to kind of attack it differently, and that's very important because on your exam, I mean, you'll have different ways to solve a differential equation. I might suggest one, but if you feel like solving it a different method, that's completely fine. It's just how you view the problem. Okay, let's get started. So in this differential equation, we want to learn how to recognize the Bernoulli equation. So I'm going to start off by rewriting this equation using Leibniz notation. So I have 2x y dy dx, right, instead of y prime equals 4x squared plus 3y squared. And in Bernoulli's equation, let's go ahead and just write that down. We have dy dx plus p of x times y equals q of x, and q of x times y raised to the n power. So we want it to look like this form if we're going to use Bernoulli. So notice that, I mean, we have our dy dx plus some continuous function times y. So that's what I want to do in this case. So this is from page 63. So I'm going to go ahead and divide both sides by, well, we can do 2x y, right, because I want my dy dx isolated. So I'm left with, right, I'm here, dy dx equals, and I'm just going to go ahead and separate the fractions. Again, if you can do this part in your head, that's fine. Again, I just want to make sure everyone's on the same page. So might as well just show every step. Okay, so just simplification here, a little bit of algebra. So we have 2x over y plus 3 halves x here and y. And if you notice in the Bernoulli equation, right, okay, so we have our dy dx, so there's my dy dx, that's a d. And it's plus, right, some continuous function times y, right, where y is in the numerator. So here my y, which is in the numerator, is here, right, not this expression. So I actually want to bring, right, this guy over, right, by subtracting that expression, and then this guy will be my q of x. So let's move this up. So I have dy dx minus 3y over 2x, and sorry, sometimes I write my y's like this, sometimes like this, I apologize if it's inconsistent, equals 2x over y, right? Or we can say 2xy to the negative 1. And you'll see why I used my negative power there. Okay, so dy dx, and remember, minus in the Bernoulli equation, we have a p of x times y, so I can rewrite this guy as plus negative 3/2 x of y. Okay, make sure your x is in the denominator, not in the numerator. Just because some students might write, you know, negative 3/2 x really quick y. Well, this is wrong, all right, sad face, because your x is in the numerator, right? This is a linear equation, or including, if you exclude the y, right? That's just a line, but this is a rational function. Okay, so we have equals, and then our 2xy to the negative 1. So here, hopefully you can see that, okay, so p of x, let's see, let's make this maybe green. So p of x and q of x. So there is my p of x, and there is my q of x, right? So let me maybe box that, right? They're functions of x, right? P of x and q of x. So here, let's just say let p of x be, or we know p of x is negative 3 over 2x, and my q of x is 2x. And note in the Bernoulli equation, okay, on page 63 of your book, we have a Bernoulli equation. Now, if either n is 0 or n equals 1, then we know our equation is linear, which is nice because we learned that in section 1.5. So if we look at our n, well, what's our n? Okay, this is our n, and our n is negative 1. So it's not 0 or 1. So it's not linear, so we can't use the integrating factor. But can we use maybe substitution and maybe transform it so that it looks linear in terms of v and x? And the question is, and the answer is actually going to be yes if you're reading the example instead of following the video, if you're able to read it on your own. So let's go ahead and do that. So let's just move this up a little bit. And whoops, isn't that cool? I love that. Okay, so let's make this a little bit bigger. So we have, okay, we're familiar with the Bernoulli equation, and the trick to the Bernoulli equation, or what should I substitute, what should I let v be? So here, whoops, okay, so I'm beginning my, substitution method that we are learning in 1.6. So I'm going to let v be, okay, so it's y to the 1 minus n, and you can see this in your book. This is equation 10. But what's my n? Well, my n is negative 1, so, I mean, that's really y equals, right, 1 minus negative 1, which we just know is y plus to the 1 plus 1, which is 2. So I'm going to let v be y squared. Okay, that's one equation. Remember when we let v be some expression, right, we still have to solve for y. So if I raise 1/2 to both sides, then I easily get, y equals v to the 1/2, right? And there's our second relationship that I'm going to use, right? And finally, we usually differentiate, right, this guy, right? We do dy dx. So maybe let's just write that here. So let's see, I'm going to do dy, right, or ddx of y, which is just dy dx. So I want to differentiate this guy, right? And remember, v is really y squared, so really using the chain rule here. So I want you to recall that dy dx, and this is why the book wrote it this way, is dy dv times dv dx. Okay, if you go back to your Calculus 1 book and you go review the chain rule, you're going to see this expression, these derivatives. And again, right, we're using dv, so that's why we're you see dv in there. And then when you differentiate this, right, just using again power rule, right, bring down the half, subtract 1, so we get v to the negative 1/2 times, right, using the chain rule, times dv dx, right, in this case v is y squared. So okay, here is our equation that we are going to use, and maybe let's just write it a little bit closer to each other. So a half v to the negative 1 times dv dx. So here's my third relationship. Okay, so now let's transform this equation, right, this differential equation of x and y, right? We're going to go from f of x, y to some other function of x and v, right, using substitution. Okay, so our differential equation, let's see, so I want to use, I'm going to use this guy right here, right, that one right there. So hopefully maybe you can write that down, and it's very, very small. Whoops. Okay, so begin substitution. So what is dy dx? Okay, dy dx, well, it is right here, right, in terms of v and x. So I'm going to write 1/2 v to the negative 1/2 dv dx, right? And again, let's see some colors here. Okay, let's do pink. So that's my dy dx, right? That's my dy dx. And I have plus negative 3/2 over x times y. Well, we know what y is, right? It's right here. Y is v to the 1/2. And again, I'm changing colors. That's my y. And equals 2xy. So 2x and then again y is just v to the 1/2, but we're raising that to the negative 1 power. Okay, so if we just, well, not really much we can do here. I'm just going to simplify one thing. Let's see, okay, so plus negative 3/2 x v to the 1/2 equals 2x v to the negative 1/2. So remember, the goal is to transform this equation by using substitution to hopefully get a differential equation that's linear. So just by simplifying this a little bit, right, and we really want our dv dx minus some p of x v. So if that's why in the book they multiplied both sides by 2v to the 1/2, right, because we're going to get a nice, we're going to get a nice 1 here. So after multiplying 2v to the 1/2, right, we produce dv dx minus 3 over xv equals 4x. Right, we have 2v to the 1/2, right, 2v to the 1/2, 2v to the 1/2. Now, if you wanted to use equation, so right on page 63, you see equation 10, right, and it says our v equals y raised to the 1 minus n can be transformed into our linear equation, which is this is what we got here. And notice there's a nice little formula for it. So dv dx plus 1 minus n, our n in this case is negative 1, so it's really 1 plus 1, which we get 2, and so we do get a 2 here. So if you want, I mean, you have a page of notes on your exam, so you can write that equation down and it, input the values. But I encourage you to learn how to use the substitution because it's going to help you, especially in the next chapter. Okay, so I'm going to stop right here because I've a couple seconds before it lets me stop at 15 minutes, and I'll continue the solution in the next video, or if you want to read the book, that's fine.